So now what we have learned so far is about the redox reaction, and we have also learned that it's about the flow of electrons, and then redox reactions are actually um, um, the oxidation reaction and the reduction reaction together. So we have to, if we look at the redox reaction, we have to split that into two half reactions. Again, the oxidation reaction and and the reduction reaction, and that is important. That is all about the information that we need to just discuss these galvanic cells or the voltaic cells. Okay. So voltaic cells, when we come here and talk about the voltaic cells or galvanic cells, whatever you want to call it, and the transfer of electrons takes place through an external circuit. Okay, so we're going to make up a circuit, and these electrons are going to transfer. And you definitely know that electrons, where the electron going to go from. Okay, so it's going to go from uh, negative to positive. Anyways, we're going to discuss that. So the reactants are separated into two half cells, as we have discussed. That two half cells means two things are going on, and we are going to give electrons to move from one place to another place. One, where the oxidation, so in our half cells, in the galvanic cells or the voltaic cells, we have two half cells, and where one cell is going to have the oxidation half reaction happening in it, and the other one is having the reduction half reaction happening into it. So two chambers in a cell, one is for the oxidation half reaction and one is for the reduction half reaction. And in other words, we can say electrons are going to be lost from one chamber and going to be gained into another chamber out of the two chambers that we are talking about, or the two half cells. You can call it a chamber, you can call it a half cell in the voltaic cells, okay? And then these two chambers are connected through a cell bridge that allows the transfer of ions to complete the circuit. Okay, otherwise the circuit will not be completed. So we need a solid bridge. The two electrodes, and there's more about solid bridge, why we need that. Okay, so we're going to discuss it later on, but let's move on to the next point. Is that the two electrodes are connected by the external circuit, where we have cathode and anode. And the cathode is the electrode where the reduction is happening. Always keep that in your mind, that cathode means reduction. Reduction means gain of electron. Okay, oxidation number is going up. That is going to be cathode. And node means oxidation reaction is happening at that electrode, and that means loss of electron is happening, and that means that the oxidation number is going down in that case. So these moving electrons, so when we complete the circuit, we have two electrodes. So the moving electrons can be used as a source of electricity. So then from the oxidation, which is anode, the electron is going to go towards the cathode, where the reduction is going to happen. And this phenomena, this moving of the electrons, can generate electrical energy. So let's look at an example. Okay, this is an example of a volumetric cells. So when we talk about that volumetric cell, voltmeter or the galvanic cell, let's discuss the copper and silver galvan cell. Let's see, this is one chamber, this is another chamber. You have anode here, you have cathode here, and this is your salt bridge. Okay, so what's going on in this is interesting, okay, and we have to pay attention to this point here. So you see the positive potential that is being generated here in volts. It means the cell is working. Positive potential has been generated, and potential is about the movement of the electrons. Moving electrons means there is a potential to generate some electrical energy, right? And electrical energy is being generated in response to the transfer of electrons from anode to cathode. So let's say, when we're talking about that, we have this cell which is copper and silver cell. We can have different types of cells. Okay, so this one is called copper, and the where is my, if I want to use that pen and things from here, let me just add it, finish this one here. Okay. to share my, let me just do that. Sharing the window, but I need to go. Actually, my computer is not working well right now. I do not know what happened to the computer, but what I'm trying to see, it's like a weird thing is going on. So looking at it and going on to the galvanic cell. So if you look at this galvanic cell, it's working well. So, and as I've said that we are talking about the copper and the silver galvanic cell, okay? Copper, so what is going to happen? So what do you see? Copper, silver is plus, and then copper is just a neutral atom, okay? So we have copper. Copper is a metal. So metal tends to gain electron, right? We know that. Okay, so we have copper as an anode here, and we have over silver, which is again a metal, and that is acting as a cathode here. Okay, what does that mean by anode and cathode? Our species here is silver. Okay, so if you look at this, it is a silver here. So this copper, you can call it a copper sheet or a copper rod, that is neutral copper atoms. Here, what do you have as a solution in the chamber? We have copper 2 nitrate solution in the chamber. Okay, so copper 2 plus ion. So when the copper is going to convert into copper ion, that's going to be copper 2 plus. Okay, okay, and then here you have silver nitrate solution. So that's going to be silver plus and then nitrate minus here. So we know already about that when we have two solutions here for the copper nitrate, and then we have silver nitrate, that's going to be copper and nitrate in the solution. So what will happen? Okay, so what is going to happen when we just make the circuit? Okay, when we complete the circuit here. Okay, so the electron will start to move from one place to another place. So what do we know about where the electrons are going to move from and where it's going to go to? We know that oxidation and reduction chambers are there. Okay, so the negative anode is where oxidation is happening, the loss of electron is happening. So we have set it up as negative anode, cathode, a copper anode, and then silver cathode. So anode, I know, is where the oxidation is going to happen. Oxidation means loss of electrons. Okay, loss of electrons. So electrons going to come out of copper. Okay, so copper, which what you see as a rod here of copper, is all neutral copper. So when we just complete the circuit, so a copper will start losing its two electrons, and then the copper is going to change into copper 2 plus, and it's going to leave this metal copper rod here, and it's going to come into the solution because it's no longer solid. Remember that ions are aqueous, so it's going to leave the rod, and the more and more copper ions will come into the solution. Okay, so okay, we know that. So that's good. But what happened? The two electrons have been released. So these electrons are going to travel from here, and they're going to go towards the anode. So what do you need? You need two silver to accept those electrons coming out of copper. So we have silver here in the solutions. These silvers are going to accept two silvers. Definitely you need two silvers for two pluses there. So the electrons came out from there, and because in the solution we have silver, so silver is going to gain those electrons, and it's going to become the solid then, right? So solid, will not be here in the aqueous condition. It's going to go and going to be deposited on the rod here. So that's also called the silver depositing on any rod. Okay, so when we have like silvery stuff and we want it to shine or want to do the polishing or the little coating of silver on that stuff, household stuff or jewelry or anything, this is how we can coat silver on a pre-existing silver metal. So that's what is going on. Okay, but in this case, in this course, what we see here is that our solution is 1 molar concentration here and 1 molar copper 2 nitrate. This is 1 molar solution of silver nitrate. So we have to keep the ratio of the cations and anions in the same concentration. So we do not want the copper and nitrate to be imbalanced here. We do not want silver and nitrate to be imbalanced here. Why? Because more and more copper ions are coming out into the solution. So we also need nitrate to go with those copper to make it a copper 2 nitrate solution. Okay, so the balance between the two ions in the compound, it needs to be balanced, and that is provided through the salt bridge. Okay, salt bridge, we're going to decide about a salt bridge, and that's going to be filled with a particular solution in it. And that solution is going to provide, let's say, if I have sodium nitrate, so I'm good with the sodium nitrate, so I need nitrate here because more coppers are coming in. So for more coppers, we need more nitrate. So then this porous plug in the salt bridge, it allows, it specifically allows nitrate ions to come out of this salt bridge and go into the solution. So when the copper ions are coming out of the rod, they're going to go into the same ratio as it is required to be balanced. Otherwise, the concentration of 1 molar solution is no longer going to be the concentration. And then if we disturb the concentration, then we are just going to disturb this entire Galvan cell. Okay. So then we need to balance the positive and negative ratio here. So while silver as a cation is going to be removed from the solution, we need more cations to keep the balance of the pluses and minuses there, right? And the sodium has been used for that purpose, which is coming from this compound. And again, the porous thing here, right? So what happens in this sodium, because this nitrate is gone to this place, the sodium is alone, so it's going to take up more and more nitrates because there's an imbalance between the silver as the silver becomes neutral by gaining the electrons coming from the copper from here, right? So the silver is going to go gain those electrons and silver is disappearing. So more nitrates are there. What we want to do is want to remove the extra nitrates from there. Okay. So they're going to go into the sodium and nitrate form, and then silver and nitrate ratio remains the same in this solution here. That's what we call the galvanic cell. So the flow of anions and flow of cations, we know, okay, the anion is going to go towards what, where, and the cation is going to go towards what in the salt bridge. So if you understand this galvanic cell, then this is the chemical reaction. For every copper losing 2 electrons, you need 2 silver ions to gain those electrons, right? And then become solid silver, and copper is losing, so copper is becoming an ion here. And that's what is going on, and that's what I tried to explain. Okay, the external wires are connected to a voltmeter, so we can look at the voltage, and that positive voltage is telling me that, okay, a lot of a process is smooth and is happening, and that tells me that the system is working, means electrons are flowing, and that is actually giving me the electrical energy as electrical potential here. So copper and silver cell again. So at the copper anode, electrons are produced, okay, and electrons flow from the anode through the voltmeter to the silver cathode. The voltmeter indicates the cell's potential, which is this. So when we talk about the electron sent enter the silver cathode, at which this is happening, as I said, that the ions are already present in the solution. So those ions are going to gain the electrons and become neutral and going to be deposited on the rod here. And then charge balance will happen as the oxidation occurs. A surplus of positive ions builds up at the anode, right? So that's why that's what we are trying to tell you. The area near the cathode becomes deficient in positive ions. So the Salt bridge is going to provide that function, supplies additional cations and anions to balance. Exactly the same thing that I tried to explain here is all written here as well. So it's going to be a repetition if I go and read that for you. So there's no need. So let's go more onto the Salt bridge. What Salt bridge is doing? The Salt bridge is a porous material consisting of a concentrated salt solution. It can either be sodium nitrate or potassium nitrate, but that serves the purpose exactly for the silver and copper cell, Galvan cell. Okay, so anions flow towards the anode to neutralize the buildup of positive charge. What does that mean? And ions flow towards the anode. This is what it is saying. Okay, so the anions in the salt solution in the salt bridge, these anions are moving towards anode, right? Why? Because more and more coppers are coming out of anode, the metal at the anode. So they need to counter that. Okay, the ratio remains the same because we want the concentration to be the same in both the chambers that you're looking at here. Chamber here on the left hand side and the chamber there on the right hand side. So the electrons enter the silver cathode at which this is happening, and when the silver from its ionic state goes to solid, it starts depositing onto the plate here. So charge balance, when you look at the copper and silver, so copper and silver here, as the oxidation occurs, the surplus of positive ions builds up at the anode, and that's what I've tried to explain for you guys. Okay. So this is again example of the salt bridge that we are looking at here. This is the salt bridge. Sodium nitrate, potassium nitrate can also be used. Okay, now the next thing is about the line notation for the volatile cell. We can just write down a shorthand format to show the galvanic cell, what I'm going to make, um, or what I have made as a galvanic cell. I can just I have a very shorthand kind of writing that can show my galvanic cell, and that's what we call line notation for the voltaic cells. And it's just important to just simplify it. Okay, simplify a cell. I am not supposed to draw that cell again and again. The species at anode, which are where the oxidation is happening, were written first. Okay, so if you are trying to write down a line notation for the voltaic cell, you're going to first write down the anode. Okay, and definitely at anode you're going to be having either copper or something else. Whatever example is for copper and silver. So our anode is copper. So we're going to just write copper first into the line notation while we are writing. This is what we call the line notation. Okay. So, so the copper, so what's happening with the copper, we're going to write down the neutral copper, and then we're going to separate it with this line, and then we're going to show that copper is becoming 2 plus. Whatever the concentration of the solution, we're going to show that as well. Okay, so that's, let's say 2 molar solution was here, so I'm going to write down the solution. So writing concentration is not so important because sometimes it's written, sometimes there's no need to write. Okay, sometimes the concentration of the ions is including, sometimes we just do not need to. So don't include spectator ions like this equation. You see the net equation, net ionic equation. We are not working with the spectator ions because they do not participate in anything. The flow of electron is between copper and silver, and that's where we are interested in. So while we're writing the line notation, the anode is going to come first and then is the cathode. Okay, so that's how we're going to write it down. And remember, these 2 lines between this to that is showing the salt bridge. So actually, if you just write it down, there's going to be copper line, copper 2 plus, and just omit the concentration, let's say, then you're going to make 2 double lines, and then you're going to write down silver from G plus is going to silver. Okay, so that's exactly you are showing the Galvan cell. So if you try to summarize galvanic cell, it's about the compartmentalization. Okay, compartmentalization. You're having 2 different chambers that, well, I call it chamber. You can call it the compartment. The oxidation and reduction half reactions into half cells and enables a spontaneous, what our compartmentalization doing is that, okay, it's or the chamber, 2 different chambers in the Galvan cell doing is that they're having oxidation reaction in one chamber, reduction reaction in one chamber, and this is going to be connected to the salt bridge, and this enables a spontaneous redox reaction to be a source of electrical energy. That's the purpose. So in one half cell, the anode oxidation occurs. In the another half cell, the cathode reduction occurs. So each half cell consists of an electrode dipped into an aqueous solution, like you were looking at it here, right? So that is the electrode dipped into the solution. And then the half cells are joined by an external wire. Electron movement will happen through the wire, and Sol bridge is important for the movement of the ion. If that is all not said, you may halt. It may halt. What may halt? The governance cell may halt. Okay, what it will stop functioning. Then the most important thing, the concept is about the potential difference. What is potential difference? It is about the flow of electron from the anode to the cathode because of the differences between their potential energies. Okay, why it's going from anode to cathode. Okay, why electrons flow from anode to cathode is because the difference between their potential energies. Electrons spontaneously flow towards the electrode with more positive electrical potential. That's spontaneous. You all have already discussed about the spontaneity of the reactions. Okay, so again, electrons spontaneously flow towards the electrode with the more positive electrical potential. So when we're talking about the electrical potential of anode, we're talking about the electrical potential of cathode, about the copper and silver. Let's right. That's what we have um, um, as the as the metal rods hanging in the solution, right? So what is the potential? So there's an entire table of looking into the potentials to decide for which is going to be an anode and which is going to be a cathode. So electrons is again, electron spontaneously flow towards the electrode with the more positive electrical potential. So it means they both can have positive potential. Means when we talk about the cathode and when we talk about the anode, they both can have positive electrical potential. If we're going to decide between which one is going to be an anode and which one is going to be a cathode, we're going to go base our decision on this statement where it says the electrons spontaneously flow towards the electrode with the more positive electrical potential. Okay, so the more towards the electrode with the more positive electrical potential. So we're going to say, okay, it means silver is more is an electrode with more positive electrical potential. That's why the electrons are flowing from copper to the silver. Okay, that's the reason. You may say, okay, why not from silver to copper? That's the reason. The potential electrical potential difference is what makes the difference. How do we know that? There's going to be a table we're going to be looking into, and then the potential differences have been tabulated, or electrical potential have been tabulated. So you're going to look at the value of the electrical potential between the copper and silver, and you will find that silver is more positive. So electric mode. So then when we are doing that, this is in volts, okay, and this is 1 volt, which is equal to 1 joules per coulomb. That is about the energy, okay. So electron motive force, while electron motive force, and we are talking about the cell potential actually, okay. What is the potential of the cell? Can electrons move? What is the electron motive force? And that tells us that how well the cell is going to work, means how much energy we can actually expect out of that cell. So the potential difference between the two electrodes in a volatile cell is what drives the electrons to move. Potential difference. Okay, what is the difference between the number between the anode and the cathode? Okay, so this is what drives the electrons to move, and this is what we call the electron motive force, EMF. Very important. So the EMF of volatile cell, okay, that we call E cell, we can also call it E cell, will be positive for any redox reaction that proceeds spontaneously. Okay, so so keep that in your mind. E cell or EMF, okay, will be positive for any redox reaction happening spontaneously. Under standard conditions, we get the standard EMF or E cells. So we already know since last chapter that whenever we are talking about the standard, whenever we are setting things on the standard conditions, then we're gonna just use this degree sign here, right? So this is non-standard E cell, and this is the standard E cell because it's going to be calculated at the standard conditions. Standard reduction potentials of many half cells have been tabulated, as I have mentioned earlier. So they are all listed for the reduction reactions. E reduction, in the sense, you're going to just look at the E reduction, E reduction, E reduction in the table, and then you can calculate. You can have the cell potential by this formula. What is the cell potential? Is the cell potential is, as we have discussed that already, right? What is the E cell? E cell is right? Is it coming from the potential difference between the two electrons? That's what we are doing here. We are getting the difference between the two electrodes. So E reduction at cathode. So E reduction is for both of these, anode and anode and cathode. We're just going to call it E reduction. Okay. It is not specified as cathode and anode in the table. It's just E reduction. You have to identify which one is your cathode, and you have to identify which one of these is your anode, right? And then you're going to put that into the equation. So that's the most important step where students actually make mistakes. They are not able to identify their cathodes in nanor, and they're going to put the values incorrectly. Whatever was supposed to be here, they're going to put that here, and that's why they're going to get the wrong E cell. Okay, so pay attention to that. For all E cell, or for all, you see E reduction are reference to the reduction of hydrogen ion. Okay, so we're going to go into the table, and you're going to say that at hydrogen, we're going to call it 0. For hydrogen ion, the reduction of the hydrogen ion, we're going to say, okay, for the E reduction in that case is 0. So everything is set from there. You talk about any ion, and that's going to be set referenced on the reduction of hydrogen ion. So changing the stoichiometric coefficient in a half reaction does not change the E reduction. So that does not have anything to do with the moles. Okay, so electron, whatever we are talking about is E cell. Okay, we are talking about the E cell. So in order to calculate E cell, we have to calculate the potential we have to look at the potential difference of cathode and the potential difference of anode here, right? That's what we call E reduction for both of them. This is the potential difference, and then gonna get the difference, and then that you are actually calculating the E cell. Okay, so the more positive, so what we are saying, we're saying that the changing the stoichiometric coefficient in half reaction does not change the E reduction. Okay, so it doesn't matter. You're just gonna get that from the table. The more positive the E reduction, the greater the driving force for reduction. Does that make sense? The more positive the E reduction, the greater the driving force for reduction, means the gain of light. So we always use the E reduction in calculation, even if the reaction is written as an oxidation. Okay, we're just telling reduction, reduction, reaction. So if you look at here, the oxidation is happening here because oxidation always happens on anode, and the reduction eventually is, or actually is happening here, right? On the cathode is what we have discussed so far. We need to go back and review that where the reduction is happening and where the oxidation is happening, right? Loss of electron. So oxidation is happening at anode. So that's why I'm going to call this is my action. But the value is always written as E reduction. It's not going to be written as E oxidation. Okay. So just keep that in mind. And that's the spin. We always use reduction in calculation, even if the reaction is written as an oxidation. So this is the table where we are interested in. Okay, so you look at what I was saying, that all the values have been referenced with hydrogen. Okay, so the potential difference of 0 for the hydrogen and moving from there. So if you look at that, see here, electrical potential is a reference to 0 at the hydrogen ion. Okay, and everything goes from there, going up positive numbers, going down is negative numbers. This is a reduction potential of what? If you're having F2 as your oxidizing agent, so what has happening to that? You're going to just decide on that. You're going to come here, you're going to pick up your number from this list here. Okay, so let's talk about an example where we are supposed to calculate E reduction from E cell. So a volatile cell is based on the half reactions. The half reactions are already given to you. Okay, so I have indium and we have bromine here. So what is happening to indium? Definitely loss of electron. So oxidation, right? What is happening to this? So when you see the electrons on the reactant side, it means the gain of electrons. So you're going to call it reduction, right? Whenever you see the electrons on the left hand, on the right hand side, on the product side, in the reaction, half reaction, then you know that it's going to be lost. The electrons are lost from this PC. That's where we're going to call it oxidation. The E cell is already given to you, which is 1.47 volts. Given that the E reduction of bromine, diatomic bromine to bromine ion is plus 1.07 volts. Calculate the E reduction for indium 3 plus to indium plus. Okay, that's what we want to do. Okay, so this is our E cell, which is already given. Here it is. Then E reduction, E reduction of what? Cathode or anode is given to you. So this is reduction. Reduction means cathode or anode. Cathode, right? Because reduction is on cathode. Oxidation is at anode. So my bromine is actually the cathode. So that comes first in the formula or in the expression. That's why I'm writing. So this is given to me, which is E cell. Then the E reduction for the cathode is given to me, which is this. And I'm supposed to calculate the E reduction for indium. And indium is anode, right? Because oxidation is happening at the indium ion. So then, guys, simple as it is. Okay. So just take it over there. We already have that. You're gonna bring that out on that side. That goes on this side, and then x is equals to this, and then you have a um, negative E cell E reduction here for the bromine, which is my cathode. Okay, so for bromine, sorry, this is for indium, which is my indium is my anode. So I have calculated this one here. So that is for right. So that's what we are looking for. 3 plus 2, 1 plus mu gain of electron. Gain of electron means reduction. Reduction means anode. So, okay, sample 7 is calculating the E cell from E reduction. So using the data from the table in the previous slide, calculate the E cell for the following voltaic cell. So we have aluminum here, we have iodine here. We have to first decide on what's going on this chemical reaction. So aluminum was solid, and from here it lost 3 electrons. So reduction is happening here. Loss of electron. Oh no, sorry. Loss of electron is oxidation. I am just as crazy as I am. Okay, sorry. That's oxidation, and what's going on to the iodine? The gain of electron is happening to the iodine, and that means it is going to be reduction. Okay, and writing it right here, it's very helpful. Reduction means it is cathode, and oxidation means it is anode. So on the anode, I will have aluminum. On the cathode, I will have. So why I need to figure that out? Because I need to put the values into the formula here. Okay. So we are calculating E cell here. It means I have to get these two numbers from the table. Okay. So if I go into the table for, let's say, cathode first, and cathode is my iodine. So I'm going to go into the table, and I'm going to come here. I'm going to get the number from here, which is 0.54, right? I selected it from there. I brought it here. So same way, I'm gonna go for aluminum. Okay, so I'm gonna go into the table, figure out what the aluminum is showing me, minus 1.66. So I'm gonna come back and I'm gonna put the minus 1.66 here. Okay, make sure that this is in negative. So make a parenthesis here, put a negative sign here. This is the negative from the formula. So do not get confused with this one. This is from the formula. Okay, so finally, when you do a simple calculation, so the trickiest thing here is again, the math is not a problem at all. The trickiest thing is to figure out what is your cathode and what is your anode. Okay, so as part this part is done, so we're going to move on to the next one, and where it says the volatile cell is based on the following two standard half reactions. This is one and this is second half reaction. E reduction for both of them is provided. Both are negative. Determine which reaction occurs at anode and the cathode and E cell. Okay, the cathode will have the reduction with the more positive in such cases. Okay, when we are looking at these two examples here, where both of them are trying to lose electrons. So remember our previous statement that talks about the more positive reduction potential is going to be the cathode, and less positive reduction potential is going to be the anode. So we determine, so if that situation is given to you, a volatile cell is based on the following two standard half reaction for the cadmium and tin, both of them. Which one is going to gain electron? Which one is going to lose electron? So where is going to be anode? Where is going to be cathode? How are we going to decide that? Only when we have given the E reductions value into the table. So we pick that up from the table and we're going to go and see what the criteria is. It's asking us to determine which reaction occurs at the anode and the cathode, um, uh, and and the ethyl, right? So if we talk about that, we first need to decide which one is going to be the cathode, which was because to calculate ethyl, we first have to define that or decide about that. So it's the statement which is the key here. It says the cathode will have the reduction with more positive. What is more positive here? That's right. So that's going to be my reduction. Reduction means cathode. That's going to be my oxidation, means anode. So as simple as that, when we have to calculate the E cell, then we're going to write down the E cell, right, is equals to cathode minus anode. So then my cathode is, I've decided for that, is minus 0.136 minus and then minus 0.403. Okay, just do the simple math and you will get your E cell here. If you have question, you can get back to me, but that should not be difficult. I just showed it to you how to set it up, right? You can get your numbers from there. So this is what we are trying to show. What we are trying to show here is oxidizing and reducing agent. What is the strongest oxidizing agent? What is going to be the strongest reducing agent? Let's say the strongest oxidants have the most positive reduction potential. Okay, and the strongest reductants have the most negative reduction potential. The strongest oxidants have the most positive reduction potential. So the positive is when you go up in the table. That's what I showed it to you, right? So the more, so like fluorine is the highest in that term, okay? So when you say the strongest oxidant is going to be the fluorine, because fluorine is the highest positive reduction potential in the table. Okay, the most negative reduction potential here is for lithium. Okay, so that's how we're going to be deciding it by looking at the table, and table should be provided to you for the exam. If not, you can have your table with you. I I do not mind. And most positive values for the reduction, most negative value are down here. So which of the following is the strongest oxidizing agent? We talk about nitrate, silver, and chromate. Nitrate is here. Silver is, we have silver here. And then chromate, which is CrO7, is here. And strongest oxidizing agent is then going to be this one, the high positive number, right, for the oxidizing agent. Which of the following is the strongest reducing agent? So we're just going to decide on based on the table, right? Where is iodine is here, iron. Iron is here, aluminum. So aluminum is going to be the strongest. Why? More negative reduction potential, if you look at that. So redox and spontaneity. How do we decide about the spontaneity? If you remember earlier in the statement, I said that the positive EMF means the reaction is spontaneous. Which reaction? The redox reaction is spontaneous, means electrons going to go at their own. They do not need extra energy to move from one place to another. Means one chamber to another chamber, one end to another end. We look at this example here again, which is E is equals to E reduction minus E oxidation. So we talk about the reduction is the loss. So that's anode. Again, oxidation is anode, right? And reduction is cathode. So a positive EMF indicates a spontaneous process, a negative EMF indicates a non-spontaneous process. As simple as that, right? So nickel and silver that we're talking about, that's the example, okay? And we just want to know what is what is my cathode and what is my anode. So what is happening to the silver in the chemical reaction, if you see here, and what is happening to the nickel. So nickel is solid, solid to this means loss of electron. Loss of electron means oxidation, and oxidation means anode. Okay, so my anode here is nickel. So whatever the value for the nickel is from the table is going to go to that number. What I'm what I'm doing here. So my anode. That's what I decided for. Anode, right? And that's then my cathode. So cathode here and anode here. Get the numbers from the table, put them in, and get your answer. So if I use my calculator to get this answer here, so that's 0.80, right? So then I have, so my number is going to be a positive number, which is 1.06 volt. And that tells me the positive EMF means that the reaction is spontaneous. Then we can relate EMF with delta G. We can relate the spontaneity of the redox process to the Gibbs free energy. Very important, right? So we have delta G, Nernst equation. Okay, so delta G for the non-standard condition, how to calculate delta G or the change in Gibbs free energy. On the standard condition, we have two expressions that we have already gone through in chapter 16. Okay, so we already know about the N is the represent the number of electrons transferred during the redox reaction, always positive. Okay, NFE, Faraday's constant. This is this constant that should be provided to you. The number is already here. Then E, the EMF of the reaction. Okay, So in order to calculate the Gibbs free energy, we need to first calculate the EMF of the reaction. So if EMF turns out to be positive, what's going to be the delta G? You already know the standard for the change in Gibbs free energy. How do you decide for the spontaneity based on the change in Gibbs free energy? So E is greater than 0, then delta G is going to be less than 0. Okay, so for positive E potential, there's going to be a negative delta G value, and that's how we're going to decide about that. The spontaneity should be um, 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 should be the same stuff for when it comes to the EMF or the Gibbs free energy. So we can use this expression here and this expression here together to find the equilibrium constant for a chemical reaction, right? So if we know that part, we can calculate this. If we can calculate this, then we can calculate this. So allow us to determine it allows us to determine the K by electrochemical means. Okay, so now we are doing the equilibrium constant through an electrochemical reaction method. So when we talk about the electron motive force, it's an intensive property. Delta G and K are extensive properties that we have already looked for. So this is example 9 that discusses that. For let's say the reaction given, what is the moles of electrons which are going to be um, uh, traveling, I will say, in this reaction, okay? Being transferred in this chemical reaction. So, and for that, you need to have a balanced chemical equation, right? So this is a balanced chemical equation, redox equation. And if you go by that, then this is what is going on, okay? So from this neutral is going, so that's exactly right now, it's the loss of electron at lead means loss means oxidation, right? Oxidation means cathode. No, oxidation means anode, so it's wrong. Oxidation means anode. Reduction means cathode. Okay, so that means my lead is anode. So we're gonna write down the two half reactions for both this species. And once we know, we're gonna have loss of electrons here. So E reduction, I'm gonna get it from the table. And then E from which the reduction potential I'm gonna get for this two half reaction, I'm gonna get that from the table. And these are the two numbers for these two half reactions. Again, we're gonna have this equation to calculate the E cell, which is important, right? Because the question is for each reaction given, for the reaction given below, what is the total number of electrons flowing, and then calculate the E based on that, which is definitely we are going to calculate that, and then we can eventually calculate the delta G at standard condition. So we first going to calculate this E cell so that we can just use the NFE equation here, right? So, so we are calculating that. We got the numbers already from the table. We plug those in that we were doing it previously the same way, and we calculated the E cell. How many electrons are flowing? See, lead is losing 2 electrons, and these 2 electrons are gained by the silver. So total flow of electron is 2 moles of electron. We're going to call them 2 moles of electron. We're going to plug that into the equation here. The Faraday constant will be provided to you. The 2 moles that you have decided for through the balanced chemical equation. If the equation is not balanced, then you already know how to balance the redox reaction, and then move and then proceed for these kind of questions, and then this is your E cell. Altogether, you have been successful in calculating the delta G at the standard conditions, okay, and that turns out to be this number. So for the reaction given, calculate the K at 298 Kelvin, okay. So then you already know that you have calculated this part here, okay. So you can just say delta E. So we have what we have done here. This is exactly equal to that, okay? And then that is exactly what we are having as this. if we just try to solve for this, that's what they are saying, that we are interested in calculating the K eventually. So then simplify to use at 298 Kelvin, right? So 298 Kelvin here, going to be using temperature. Okay, then you have Faraday's constant. You have this gas constant that should also be provided to you. So if you have all that stuff, temperature and all that stuff, you're going to solve it for that. And then eventually you're going to get this number 0.0592 over n. Okay, and then you're going to take this log k and then bring this stuff on the side, so that's going to go upside down, and then log k is equals to this e value n over 0.0592 volts. So your n is 2, that you're going to plug that into it. Then your e cell is going to be this, which is 0.93. Okay, so So let's do that, okay? So what it says is, for the reaction given, calculate the K at 298 kelvins. This is the reaction that we are discussing, and we have already discussed this reaction here as well, right? So what we have done so far is we have been able to calculate the E cell, which is this number here. And we were also able to calculate the delta G at a standard condition. So we can just skip this part because we have already calculated the E here. So we're going to bring that. So just forget this part. We have already used this, and we have already used this E value here, and we have calculated the delta G naught. So when we have delta G naught from the previous example here, which is minus 200,000 joules, I can bring that out here, minus 200,000. That the weird thing that was happening earlier started happening again, is equals to, what is the value of R? I'm going to put that value in. What is the value of R? I'll be showing the value of R somewhere, which is the gas constant, right? And then the temperature is 298 Kelvin. We're going to get that the value of R, so from somewhere. Let me just figure that out. It is somewhere here that I can pick up for you guys. Okay, so this is another derivation that is valid for where we have the E cell directly and the number of mole of electron passing into the chemical reaction, to the redox reaction. So that is one thing that we can use. Okay, so we can just simplify um, our expression to calculate the K, because we know G is equals 2 minus RTL in K. And then this is an expression for delta G where the electrochemical means are going to be used. This is the one that we have been looking for from the thermodynamics. So we can just solve for another expression, which is here. Or we can also use the same expression if the delta G value has been calculated through the electrochemical means, right? So if that has been calculated through the electrochemical means, we have to go into the electrochemical. Okay, so if we go into the electrochemical means, we can just use the previous expression from the delta G naught is equals to minus RTL in K, and then we can drive for this one. So minus NFE dot is equals to here is equals to minus RTL and K, and then solving it for when you have your gas constant as this, and you multiply it with the 298 and try to solve that for. So what I'm gonna do, I'm gonna take the um, I'm gonna take my RT and F separate. Okay, so I'm gonna take the RT F separate, RT and F as a separate thing, and that ends up on this 0.0592 volts over N. Okay, and log K. And this is where I'm interested in log K, right? When I'm talking about the log K, then I'm going to put these numbers in that I've already calculated previously right here. So then I'm going to plug the number 2 here. Let's do it here. I'm doing it. So that's going to be, and that's exactly in your book as well. So 2 over point 0.05. Because I'm calculating K here, so I'm just going to avoid all the units here. At the end, I'm not going to put units anyways, right? So then times is equals to 2.93 volts here. Okay, that's somehow it's going to look like this. Okay, so then I will try to solve this, and I will see that what I can get out of that. So if you go into your 0.93, and actually the solution that we are looking for, can just we can just go into the book and we can figure that out right there. Okay, so if you go there and we try to do that equation derivation through the electrochemical means here, right? That's exactly what we have, and we can try, and we want to solve for K, and then we have this thing here. Okay, so that entire thing, if we want to just solve, so when we solve it here, right here, then we can just bring everything on top here. Okay, the N is going to be um, going to up, and it's going to multiply with that. So I'm going to do what? I'm going to take this E, because that's going to go on that side. So that's going to go like, um, then you will have this thing here. Okay, exactly like this. You have sorted out, and then this is log K. Okay, it means if you're going to get rid of log, then K is equals to 10 to the power of all of that. Okay, all of that here, whatever you have here, it's going to go here, and then when you take the 10 to the power of all that stuff, then that helps you get what you are trying to get here. So then look at this one here. Okay, so this is exactly how we are going to get our 42, like 10 to the power this right here, up to the base 10. The 10 to the power of entire stuff here, 2 times whatever the volt is for the E, and then this is stuff. So I'm gonna go and do the same thing here in our example. And if I do it with the calculator, by keeping things the same way that we have it in the example in the book, and I've intentionally showed it to you guys. So if you're getting confused, you can just directly go into the book and get it out from there. So that's my 2, right? I did that earlier as well. You can put E here, you can put E there, doesn't matter. And then your E cell was 0.93, and that is going to be divided by 0.0592. Okay, I'm going to quickly do that and see what I get out of that. 0.93 times 2, and that's divided by 0.0592. So that my number turns out to be finally my number stands because that's 10 to the power this in my calculator. So then the k is going to be um, k is going to be a very large number. We already know that it's spontaneous, means a very large k is going is expected, right? There's going to be 2.6 times 10 to the power 31. Huge value for k. That means my reaction is all the way on the right hand side already because it was very spontaneous. Okay, so you can work on that one and let me know if you guys have any trouble in that. You can always send me questions on Remind. I will try to help you out with that. EMF at non-standard conditions. Again, we talk about the standard and non-standard conditions. Then, if you recall it from the thermodynamics chapter, we have used the expressions to adjust the values at non-standard conditions. And so we're going to take the advantage of the values calculated at the um, standard conditions. And how do we calculate that on the standard conditions? Then again, we just equalize things, try to equal things accordingly, according to the electrochemical energy. So that's the exact thing equal to delta G, and that's exactly the thing equal to delta G at the standard conditions plus RT, ln Q. That brings us to another equation, and that equation is E for the calculation of the E cell. Okay, so a calculation for the E cell under non-standard conditions. Okay, non-standard conditions. We're going to take account of the E at the standard conditions, right? Number of electrons flowing in the chemical reaction. This number here that comes out of your R and T for 298 temperature. Okay, and log example, this is exactly for 298. Keep that in your mind. So log of the Q. So as the concentration of the reactants drop, Q increases, and we know that at Q is increasing. As the Q increases, the E is going to decrease. Okay, and then at equilibrium, electron motive force, E cell, and delta G is uh, going to be, it becomes zero. Okay, it's going to be equal to zero. So that's what I'm exactly trying to say here. The relation between the E cell and the log Q for the zinc copper cell. So see here, you have electrical potential here as 1.10. So the Q is the ratio of your zinc ions over your copper ions here. Okay, cell can do less work here because the reaction has already been converted to all of on has been gone to the product side already. So the Q is large than one. Here Q is the smallest one. The cell is working efficiently. It can do more work. So this is the life of the cell as well, right? So it's gonna go on that side. It's gonna go and the life of the cell. So this is the potential 1.10 right here. Gonna decide from here that the Q is 1. You know already the Q is 1. Then we're talking about the equilibrium ratio is 1, right? So the at equilibrium, the E cell is this. And that's what we were saying that, oh, why? Non-standard E is equals to 0 at equilibrium. Let's move on to that one. That's the standard E cell that we are talking about. So if the reaction starts with zinc less than copper, Q is going to be less than 1 as you see here, right? Then E is higher than the standard cell potential that we are talking about. As the reaction proceeds, copper decreases and zinc increases, so the E drops finally, okay, and then eventually E will stop, okay. So eventually the system reaches equilibrium and the cell can no longer do work. If we talk about that, we bring a Nernst equation back into this example. If the standard electric potential for the following reaction is this, what is the EMF when aluminum 3 plus is equals to this number in molar concentration? And this is the concentration of the iodide ions. Okay, so this is your chemical equation here, which is balanced. So what you're going to calculate, you're going to calculate the EMF at non-standard conditions. So you need that in non-standard condition first. So we can go into the table and we can just quickly calculate that, right? So that turns out to be this number, but this has already been given to us, right? So we do not need to. So E naught for the following reaction is given to us. I'm going to plug that in. This is for the RNT at 298, right? Temperature 298 Kelvin. The number of electrons flowing in this reaction is total 6 electrons. You can see here, right? 2 aluminum, each 3 plus, it means 6 electrons total. So log of this ratio, right? Aqueous things only, not the solid stuff. That's it, right? It's just multiplication of the two. We're gonna go move forward from here. We're gonna just divide it by that. You're gonna get that number, and then this is happening here. Raised to the powers, right? From the balanced chemical equation. Do not forget that. So this is how we are trying to simplify that. And then we're going to bring that into this number here, okay? So we took the log of that, and that turned out to be that, and multiplication turned out to be this. And then eventually this is what our E cell at non-standard conditions. And this is again the relationship between the values of delta G naught E cell. So when the delta G is 0, K is 1, E cell is going to be 0 at that point. Okay, and at equilibrium, talking about the standard electrical potential. So guys, so when we have delta G is equals to is less than 0, negative value is spontaneous. When it's spontaneous, E cell is always greater than 0. That's what we have looked at in this example. That's spontaneous. That's why E cell is always greater than 0. Okay, so at equilibrium that becomes 0. The K is equals to 1, and then delta G will also be 0. When it's non-spontaneous, it's not going to go at its own, then you're going to have a positive delta G value, means you're going to say non-spontaneous, means your E cell is negative, and it means that your K value is also a very small number, less than 1. It means reaction is not proceeding in that direction. So these are the relationships that we have been looking for. I've been discussing that if we know this, we can calculate that. If we know that, we can calculate this. So this goes into this triangle that knowing things, we can know the other stuff. So if delta G naught is known, we can use the same equation as we have been using it earlier to calculate the K, or we can go through the electrochemical means as well, as it has been shown in your book. So, but if you know the delta G at a standard condition, you can actually calculate the electrical potential of the cell at a standard condition by using this equation. So that's what it is. This triangle is all talking about. This triangle is talking about. Okay, so the last thing in this chapter is about the concentration cell. What is about the concentration cell is about the voltaic cells where the anode and the cathode are in contact with the same species of the different concentration. Okay, even though the cell at a standard condition would be the same, they operate because the concentration are different. Earlier we have looked at the same concentration in two chambers. That's not the case here. So oxidation occurs in more diluted solution, and that's what we're going to call it anode. Reduction occurs in the more concentrated solution. At that point, we're going to consider it as cathode. So just look at concentration cells. What the difference is, if you look at this concentration cell here, we have two half reactions going on. Oxidation reaction is this. Reduction half reaction is this. Okay, these are just the same electrodes, copper and copper. What is the difference here? Is about the concentration of the solutions in two chambers. Okay, this, when you have the same electrode, if the concentrations are not different, the cell is not going to work. Okay, see, at one point when this chamber this cell will start working, that we work, this is what we call the concentration cell. We have less concentration here, we have more concentration here of the solution. Okay, so what will happen? So this less concentration is going to work as anode, the more concentration is going to work as cathode. Anode means loss of electron. So from here, the loss of electron will happen. Okay. So loss of electron will give you more of copper 2 plus. So the concentration of the copper 2 plus is eventually going to increase slowly. Okay. And then the electron is going to come out and going to move towards the cathode. So this is going to accept these electrons are going to be accepted by the copper already present in the high concentration. So then copper becomes solid and going to be deposited on this rod here. It means you're going to get rid of the copper ions from here. So the concentration is going to go down here eventually. So what is happening? The concentration, as the cell starts working, the concentration is going to go up here and the concentration is going to go down here. And there will be a point then both the chamber is going to get the same concentration of copper. What you see, the copper is coming out of this here as we tried to show it here. So that's why you see the reduce in the mass of that copper solid metal electrode, and then it's being deposited here. So that's where you're going to see that it's more bulky stuff being deposited on this electrode, and that's how the concentration of the two chamber will become zero. Will be same after some time, and that's where the cell will stop working. It's no longer a concentration cell. Okay, so what they are trying to say here is this. Okay, overall cell reaction when it becomes 1.1, that was zero point 0.1 molar and that was 1 molar concentration cell. So E cell is going to be greater than zero as long as the half cell concentrations are different. So the cell is no longer able to do work once the concentrations are equal. Electrolytic cell is as simple as that: electroplating, electrolysis of water to produce hydrogen and oxygen, and then recharging of batteries. We can talk about that, but before we go, it's just simple stuff that I've just discussed in points. So you can read it at your end and understand it's not big. Similar to the voltaic cell in setup, but E cell is negative here. Okay, that's what we call, because we are giving more energy to to have this electrolytic cell happen. Okay, if you are talking about the splitting of water to produce hydrogen and oxygen, you have to give more energy to it. So that's just one of the examples. Okay, then do try these and then you're good.